Hi, this is going to be a multi-part video that's going to be talking about using the fundamental theorem of calculus to evaluate definite integrals. And all of these examples are going to relate to content in section 5.7 of your book. So part one that we're going to be talking about is how in the world could you end up with a negative number as the value of an integral, and what would that mean, considering the fact that we've tied the idea of the integral to area under the curve. So what I'd like you to start with at this point is actually just doing an example. On your paper, what I'd like you to do is try to evaluate the following definite integral. You're going to evaluate the integral from 0 to pi of sine x dx. Pause the video for just a minute and go ahead and evaluate that. All right, if you've tried this integral, what you should come up with is that the answer is 2. If you're not sure why, let's go ahead and take a look at it and see if we can figure out why the answer is 2. If I evaluate this particular integral, I'm going to erase the answer for just a minute. The first thing that I want to do is remember what I would have to differentiate to end up with sine x. We know it's going to be cosine x, but the derivative of cosine is actually the opposite of sine. So in this case, we could say the integral of sine is going to be the opposite of cosine x. And then I draw this vertical line to represent and to show the limits of integration from 0 to pi. Don't forget that once you've evaluated the integral, we use this negative or this vertical line to show the limits of integration. Now we're going to use the fundamental theorem and evaluate the function cosine x, opposite cosine x, at pi and at 0, and subtract the 2. So we're going to get the opposite of cosine pi minus the opposite of cosine of 0. Notice all the negatives running around. The negative in the middle, that's right here, is always between the two functions. The other two negatives come from the fact that this particular function is negative when you evaluate the integral. Okay, so now we simply have to actually do the evaluation. The value of cosine pi is -1, but I'm taking the opposite of -1 minus, and now we have another negative. The cosine of 0 is 1. So notice that all these negatives sort of cancel each other out here, and we end up adding 1 plus 1, which is still 2. Now keeping that in mind, we're going to try another example. In this case, we're going to evaluate the integral from -3 pi over 2 to -pi over 2 of cosine x dx. Now in this particular case, you might want to pause the video, write this integral down, and give it a shot and see what you get. Okay, so in this particular case, we're going to evaluate the integral of cosine x. Keeping in mind what we found out from the last example, this should be sine x evaluated at the two values, -pi over 2, -3 pi over 2. If we go ahead and plug in those values, we're going to get the sine of -pi over 2 minus the sine of -3 pi over 2. This is really where the fundamental theorem is being used. Now if you have a little trouble with these values, remember that the sine of -pi over 2 is the same as the sine of 3 pi over 2. We're at the bottom of the unit circle. And that the sine of -3 pi over 2 is the same as the sine of pi over 2 at the top of the circle. In either case, the sine of 3 pi over 2 is -1 minus the sine of pi over 2, which is 1. So we get -2. Now how does that make sense? It doesn't make sense when you just do it in this case because you're thinking, well, how in the world do I get a negative number? I'm going to erase this, and I'm actually going to add in a picture of the curve that we're talking about. Here it is. All right, so at this point, we have this particular function. This is our, normal cosine x function. But I want you to notice in this case that really where we're taking the integral is from this value right here to this value here. So in other words, the area that we're talking about is all under the curve, or under the x-axis. Notice that all of it falls below that particular region. And so in this particular case, we have a negative area because we are below the x-axis. That's going to tell us something about what happens when we get the value of an integral like this. Let's kind of take a look at another one of these that might seem kind of funny. This time, we're going to try taking the integral from 2 to 0 of x to the 4th dx. So this time we're using our power rule in reverse. So we're going to have x to the 5th divided by 5 evaluated from 2 to 0. Using the fundamental theorem, we're going to plug in 0 to the 5th over 5 minus 2 to the 5th over 5. And if you'll notice, this first term, of course, is just 0. And so we have negative, again, 32 fifths, or negative 6.4. And you might say, but x to the 4th is all found above the x-axis. So how in the world could we have a negative area in this case? Well, you may have noticed that the limits of integration look a little funny here. Normally, we would have the 0 down at the bottom where the 2 is, and normally we would have the 2 up here where the 0 is. They seem to be reversed. So when we reverse the limits of integration, what ends up happening is that it's like we're taking our delta x that we're using to compute the Riemann sum, and we're making it negative. Because it's like we're counting sort of backwards. And what that does is it makes the Riemann sum that we're calculating in that case less than 0. So even though this particular area is found above the x-axis, in this case, the value of the integral, the way it's being calculated, still comes out to be a negative number. Okay, one more. Let's try the integral from 4 to 1 of negative 5 dx. Now think about this for a minute. Negative 5 would be a function that would be represented by a horizontal line 5 units below the x-axis. But notice how the limits of integration look a little bit backwards because we have the smaller number on top, the bigger number on bottom. So if you think about it, normally we would expect this number to come out negative, but because the limits of integration have been switched, it may come out to be positive. Let's find out what happens. If we simply integrate in this case, since we're integrating a constant, all we're going to end up with is negative 5 times x. Think about it, if you took the derivative of that, you'd get your negative 5 back. We're going to evaluate that from 1 to 4. And so in this case, we're going to have negative 5 times 1 minus negative 5 times 4. Again, being really careful with the signs. And we get negative 5 plus 20, or positive 15. So again, because in this case, even though the area represented would be below the x-axis, because we switched the limits of integration, the value of the integral comes out to be positive. Okay, we will continue this discussion in part 2 of the video.